A jet engine is a reaction engine discharging a fast-moving jet that generates thrust by jet propulsion in accordance with Newton's laws of motion. This broad definition of jet engines includes turbojets, turbofans, rockets, ramjets, and pulse jets. In general, jet engines are combustion engines, but non-combusting forms also exist. In common parlance, the term jet engine loosely refers to an internal combustion air-breathing jet engine. These typically consist of an engine with a rotary air compressor powered by a turbine, with the leftover power providing thrust via a propelling nozzle. Jet aircraft use these types of engines for long-distance travel. Early jet aircraft used turbojet engines, which were relatively inefficient for subsonic flight. Modern subsonic jet aircraft usually use high-bypass turbofan engines. These engines offer high speed and greater fuel efficiency than piston and propeller aero engines over long distances. History. Jet engines date back to the invention of the eole pile before the 1st century AD. This device directed steam power through two nozzles to cause a sphere to spin rapidly on its axis. So far as is known, it did not supply mechanical power, and the potential practical applications of this invention did not receive recognition. Instead, it was seen as a curiosity. Jet propulsion only gained practical applications with the invention of the gunpowder-powered rocket by the Chinese in the 13th century as a type of firework, and gradually progressed to propel formidable weaponry. However, although very powerful, at reasonable flight speeds, rockets are very inefficient, and so jet propulsion technology stalled for hundreds of years. The earliest attempts at air-breathing jet engines were hybrid designs in which an external power source first compressed air, which was then mixed with fuel and burned for jet thrust. In one such system, called a thermojet by Secondo Campini but more commonly, motorjet, the air was compressed by a fan driven by a conventional piston engine. Examples of this type of design were the Caproni Campini N1, and the Japanese Su-11 engine intended to power OK kamikaze planes towards the end of World War II. None were entirely successful, and the N1 ended up being slower than the same design with a traditional engine and propeller combination. Even before the start of World War II, engineers were beginning to realize that engines driving propellers were self-limiting in terms of the maximum performance which could be attained. The limit was due to issues related to propeller efficiency, which declined as blade tips approached the speed of sound. If aircraft performance were ever to increase beyond such a barrier, a way would have to be found to use a different propulsion mechanism. This was the motivation behind the development of the gas turbine engine, commonly called a jet engine. The key to a practical jet engine was the gas turbine, used to extract energy from the engine itself to drive the compressor. The gas turbine was not an idea developed in the 1930s. The patent for a stationary turbine was granted to John Barber in England in 1791. The first gas turbine to successfully run self-sustaining was built in 1903 by Norwegian engineer Egidius Selling. Limitations in design and practical engineering and metallurgy prevented such engines reaching manufacture. The main problems were safety, reliability, weight and, especially, sustained operation. The first patent for using a gas turbine to power an aircraft was filed in 1921 by Frenchman Maxime Guillaume. His engine was an axial flow turbojet. Alan Arnold Griffith published an aerodynamic theory of turbine design in 1926, leading to experimental work at the RAE. In 1928, AF College Cranwell cadet Frank Whittle formally submitted his ideas for a turbojet to his superiors. In October 1929 he developed his ideas further. On 16 January 1930 in England, Whittle submitted his first patent. The patent showed a two-stage axial compressor feeding a single-sided centrifugal compressor. Practical axial compressors were made possible by ideas from A. Griffith in a seminal paper in 1926. Whittle would later concentrate on the simpler centrifugal compressor only, for a variety of practical reasons. Whittle had his first engine running in April 1937. It was liquid-fueled, and included a self-contained fuel pump. Whittle's team experienced near panic when the engine would not stop accelerating even after the fuel was switched off. It turned out that fuel had leaked into the engine and accumulated in pools, so the engine would not stop until all the leaked fuel had burned off. Whittle was unable to interest the government in his invention, and development continued at a slow pace. In 1935, Hans von Owen started work on a similar design in Germany, initially unaware of Whittle's work. Von Owen's first device was strictly experimental and could run only under external power, but he was able to demonstrate the basic concept. Owen was then introduced to Ernst Heinkel, one of the larger aircraft industrialists of the day, who immediately saw the promise of the design. Heinkel had recently purchased the Herth Engine Company, and Owen and his master machinist Max Hahn were set up there as a new division of the Herth Company. They had their first HES-1 centrifugal engine running by September 1937. Unlike Whittle's design, Owen used hydrogen as fuel, supplied under external pressure. Their subsequent designs culminated in the gasoline-fueled HES-3 of 1,100 lbf, which was fitted to Heinkel's simple and compact He-178 airframe and flown by Erich Warsitz in the early morning of August 27, 1939, from Rostock-Marienheer Aerodrome, an impressively short time for development. The He-178 was the world's first jet plane. Austrian Anselm Franz of Junkers engine division introduced the axial flow compressor in their jet engine. Jumo was assigned the next engine number in the RLM 109-0XX numbering sequence for gas turbine aircraft power plants, 004, and the result was the Jumo 004 engine. After many lesser technical difficulties were solved, mass production of this engine started in 1944 as a power plant for the world's first jet fighter aircraft, the Messerschmitt Me 262. A variety of reasons conspired to delay the engine's availability, causing the fighter to arrive too late to improve Germany's position in World War II. Nonetheless, it will be remembered as the first use of jet engines in service. Meanwhile, in Britain the Gloucester E-28-39 had its maiden flight on 15 May 1941 and the Gloucester Meteor finally entered service with the RAF in July 1944. Following the end of the war, the German jet aircraft and jet engines were extensively studied by the victorious Allies and contributed to work on early Soviet and US jet fighters. The legacy of the axial flow engine is seen in the fact that practically all jet engines on fixed-wing aircraft have had some inspiration from this design. By the 1950s, the jet engine was almost universal in combat aircraft, with the exception of cargo, liaison and other specialty types. By this point, some of the British designs were already cleared for civilian use, and had appeared on early models like the de Havilland Comet and Avro Canada jetliner. By the 1960s, all large civilian aircraft were also jet-powered, leaving the piston engine in low-cost niche roles such as cargo flights. The efficiency of turbojet engines was still rather worse than piston engines, but by the 1970s, with the advent of high-bypass turbofan jet engines, fuel efficiency was about the same as the best piston and propeller engines. Uses: jet engines power aircraft, cruise missiles, and unmanned aerial vehicles. In the form of rocket engines, they power fireworks, model rocketry, spaceflight, and military missiles. Jet engines have propelled high-speed cars, particularly drag races, with the all-time record held by a rocket car. A turbofan-powered car, Thrust SSC, currently holds the land speed record. Jet engine designs are frequently modified for non-aircraft applications, as industrial gas turbines or marine power plants. These are used in electrical power generation, for powering water, natural gas, or oil pumps, and providing propulsion for ships and locomotives. Industrial gas turbines can create up to 50,000 shaft horsepower. Many of these engines are derived from older military turbojets such as the Pratt & Whitney J57 and J75 models. There is also a derivative of the P&W JT8D low-bypass turbofan that creates up to 35,000 HP. Jet engines are also sometimes developed into, or share certain components such as engine cores, with turboshaft and turboprop engines, which are forms of gas turbine engines that are typically used to power helicopters and some propeller-driven aircraft types. There are a large number of different types of jet engines, all of which achieve forward thrust from the principle of jet propulsion. Air-breathing commonly aircraft are propelled by air-breathing jet engines. Most air-breathing jet engines that are in use are turbofan jet engines, which give good efficiency at speeds just below the speed of sound. Turbine-powered gas turbines are rotary engines that extract energy from a flow of combustion gas. They have an upstream compressor coupled to a downstream turbine with a combustion chamber in between. In aircraft engines, those three core components are often called the gas generator. There are many different variations of gas turbines, but they all use a gas generator system of some type. Turbojet. A turbojet engine is a gas turbine engine that works by compressing air with an inlet and a compressor. The compressor is powered by the turbine, which extracts energy from the expanding gas passing through it. The engine converts internal energy in the fuel to kinetic energy in the exhaust, producing thrust. All the air ingested by the inlet is passed through the compressor, combustor, and turbine, unlike the turbofan engine described below. Turbofan. A turbofan engine is a gas turbine engine that is very similar to a turbojet. Like a turbojet, it uses the gas generator core to convert internal energy and fuel to kinetic energy in the exhaust. Turbofans differ from turbojets in that they have an additional component, a fan. Like the compressor, the fan is powered by the turbine section of the engine. Unlike the turbojet, some of the flow accelerated by the fan bypasses the gas generator core of the engine and is exhausted through a nozzle. The bypassed flow is at lower velocities, but a higher mass, making thrust produced by the fan more efficient than thrust produced by the core. Turbofans are generally more efficient than turbojets at subsonic speeds, but they have a larger frontal area which generates more drag. There are two general types of turbofan engines, low bypass and high bypass. Low bypass turbofans have a bypass ratio of around 2:1 or less, meaning that for each kilogram of air that passes through the core of the engine, 2 kilograms or less of air bypass the core. Low bypass turbofans often use a mixed exhaust nozzle, meaning that the bypassed flow and the core flow exit from the same nozzle. High bypass turbofans have larger bypass ratios, sometimes on the order of 5:1 or 6:1. These turbofans can produce much more thrust than low bypass turbofans or turbojets because of the large mass of air that the fan can accelerate, and are often more fuel efficient than low bypass turbofans or turbojets. Turboprop and turboshaft. Turboprop engines are jet engine derivatives, still gas turbines, that extract work from the hot exhaust jet to turn a rotating shaft, which is then used to produce thrust by some other means. While not strictly jet engines in that they rely on an auxiliary mechanism to produce thrust, turboprops are very similar to other turbine-based jet engines, and are often described as such. In turboprop engines, a portion of the engine's thrust is produced by spinning a propeller, rather than relying solely on high-speed jet exhaust. As their jet thrust is augmented by a propeller, turboprops are occasionally referred to as a type of hybrid jet engine. They are quite similar to turbofans in many respects, except that they use a traditional propeller to provide the majority of thrust, rather than a ducted fan. Both fans and propellers are powered the same way, although most turboprops use gear reduction between the turbine and the propeller. While many turboprops generate the majority of their thrust with the propeller, the hot jet exhaust is an important design point, and maximum thrust is obtained by matching thrust contributions of the propeller to the hot jet. Turboprops generally have better performance than turbojets or turbofans at low speeds where propeller efficiency is high, but become increasingly noisy and inefficient at high speeds. Turboshaft engines are very similar to turboprops, differing in that nearly all energy in the exhaust is extracted to spin the rotating shaft, which is used to power machinery rather than a propeller. They therefore generate little to no jet thrust and are often used to power helicopters. Profan. A profan engine is a jet engine that uses its gas generator to power an exposed fan, similar to turboprop engines. Like turboprop engines, profans generate most of their thrust from the propeller and not the exhaust jet. The primary difference between turboprop and profan design is that the propeller blades on a profan are highly swept to allow them to operate at speeds around Mach 0.8, which is competitive with modern commercial turbofans. These engines have the fuel efficiency advantages of turboprops with the performance capability of commercial turbofans. While significant research and testing has been conducted on profans, no profan engines have entered production. Ram-powered jet engines are air-breathing engines similar to gas turbine engines, and they both follow the Brayton cycle. Gas turbine and ram-powered engines differ, however, in how they compress the incoming airflow. Whereas gas turbine engines use axial or centrifugal compressors to compress incoming air, ram engines rely only on air compressed through the inlet or diffuser. Ram-powered engines are considered the most simple type of air-breathing jet engine because they can contain no moving parts. Ramjets are the most basic type of ram-powered jet engines. They consist of three sections: an inlet to compress incoming air, a combustor to inject and combust fuel, and a nozzle to expel the hot gases and produce thrust. Ramjets require a relatively high speed to efficiently compress the incoming air, so ramjets cannot operate at a standstill and they are most efficient at supersonic speeds. A key trait of ramjet engines is that combustion is done at subsonic speeds. The supersonic incoming air is dramatically slowed through the inlay, where it is then combusted at the much slower, subsonic, speeds. The faster the incoming air is, however, the less efficient it becomes to slow it to subsonic speeds. Therefore, ramjet engines are limited to approximately Mach 5. Scramjets are mechanically very similar to ramjets. Like a ramjet, they consist of an inlay, a combustor, and a nozzle. The primary difference between ramjets and scramjets is that scramjets do not slow the oncoming airflow to subsonic speeds for combustion. They use supersonic combustion instead. The name scramjet comes from supersonic combusting ramjet. Since scramjets use supersonic combustion, they can operate at speeds above Mach 6, where traditional ramjets are too inefficient. Another difference between ramjets and scramjets comes from how each type of engine compresses the oncoming airflow. While the inlet provides most of the compression for ramjets, the high speeds at which scramjets operate allow them to take advantage of the compression generated by shock waves, primarily oblique shocks. Very few scramjet engines have ever been built and flown. In May 2010, the Boeing X-51 set the endurance record for the longest scramjet burn at over 200 seconds. Non-continuous combustion rocket. The rocket engine uses the same basic physical principles as the jet engine for propulsion via thrust, but is distinct in that it does not require atmospheric air to provide oxygen. The rocket carries all components of the reaction mass. This allows them to operate at arbitrary altitudes and in space. This type of engine is used for launching satellites, space exploration and manned access, and permitted landing on the Moon in 1969. Rocket engines are used for high-altitude flights. or anywhere where very high accelerations are needed, since rocket engines themselves have a very high thrust-to-weight ratio. However, the high exhaust speed and the heavier, oxidizer-rich propellant results in far more propellant use than turbofans. Even so, at extremely high speeds they become energy efficient. An approximate equation for the net thrust of a rocket engine is, whereas the net thrust is the specific impulse, is a standard gravity, is the propellant flow in kilogram per second, is the cross-sectional area at the exit of the exhaust nozzle, and is the atmospheric pressure. Hybrid combined cycle engines simultaneously use two or more different jet engine operating principles. Waterjet. A waterjet, or pump jet, is a marine propulsion system that utilizes a jet of water. The mechanical arrangement may be a ducted propeller with nozzle, or a centrifugal compressor and nozzle.